Hello, and welcome to my talk, The Value of Design in OpenTelemetry. My name's Ted. I'm Ted Suo on the internet. I'm one of the co-founders of the OpenTelemetry project and also one of the system architects. And what I want to talk to you about today is the value that OpenTelemetry provides. Now, normally when I talk about value in OpenTelemetry, I'm talking about tracing and metrics and how if you combine them together into a single stream, you can cross-index them, and that correlation provides all kinds of extra value. And it's all based on context propagation, which is super awesome. But that's not what I'm talking about today. I have other talks on that subject. I just recently completed a great series on context propagation. I recommend you look that up if this is what you're after. But today, I want to talk about a different problem that OpenTelemetry solves, which is that instrumenting open source software sucks. It's so hard. You might think it's easy, right? Like you've got your library, your super awesome open source library, and you want it to log an error. So what could be difficult about that? Everything, it turns out, is difficult about that. Like, where do you even begin? Like, how do you even pick how you're going to do this? How are you going to pick a logging library? How are you going to pick a metrics library? You can't pick because it's not your job to pick. The application owner who's installing your library picks the answers to these questions. You don't pick them. And you don't know what they picked. There's too much choice here, right? Like, standard out is an option, but it's often a sad option, and most people don't pick that these days. Certainly no one picks that for their metrics or their tracing. So you still need to tell them what your library is doing, but you don't know how to tell them. And this just sucks. It's terrible. I encounter this every time I write a piece of open source software, and it was one of the motivators for me to help start the OpenTelemetry project. So how do we fix this? The answer is decomposition. Let's pull these problems apart and see how we can put them back together in a way that allows us to match all of these requirements. So problem number one, shared libraries need to support many applications, right? Like this is the point of open source software, is to get installed in lots of different applications. But the problem is if you want to instrument your software library, that instrumentation is usually tied to an implementation. So someone writes a data storage system for telemetry data like metrics, and then they write some clients that lets you send information to that data storage system. And then you have to use those clients to instrument your software. But libraries, as we said, they can't impose a choice of implementation here. So instrumentation must not require an implementation. Okay, that's going to be requirement number one. So great. We have our instrumentation here, and no matter how we do it, we have to provide some flexibility in the implementation. But that's not the only thing we have to do. Not only does software have to compose into many different applications, it has to do that while composing with many other libraries, which will also want to instrument themselves. And this is where dependencies ruin everything, right? Because libraries can't synchronize with each other, which means the instrumentation I write in my library is not necessarily going to be at the same version of the instrumentation that you write in your library. And not only does my instrumentation get out of sync with your instrumentation, any dependency that my instrumentation takes on may conflict with any other dependency that any other software may have installed, right? So if my tracing client wants to use gRPC, that's fine. gRPC is a reasonable choice. But if any other software in that system has installed any incompatible version of gRPC, there's now a dependency conflict. And if you foist that dependency conflict on a library so that that library can't get installed because the instrumentation it chose to use doesn't compose well with other libraries, then that's going to be a real impediment. So we don't want that. Instrumentation can never be the reason that a software library can't be installed in a system, which means instrumentation can never create dependency conflicts, ever. So that's great. It's another tough one. Are we done yet? No, of course we're not done yet. not only does instrumentation need to avoid dependency conflicts, it also needs to avoid security issues and bugs. And the only way to do that is to update. We're living in the 21st century where security problems in open source are a real thing. We've seen real issues and real harm occur because software was out of date or contained a vulnerability. And so we need to take this seriously and ensure that applications are always on the latest version of the software that we provide. Okay, so that seems simple enough, but what if there's old instrumentation that no longer works with the latest version of OpenTelemetry? That means they're going to be blocked by that instrumentation. This is bad enough when you own the instrumentation and have to go out and rewrite it all, but if that instrumentation is in somebody else's library, then you can't easily get at it. So this is a real problem. This means that instrumentation must always be backwards compatible to ensure that any new version of OpenTelemetry will work with existing instrumentation that's already out there. So in short, OpenTelemetry must be composable, it must play well with all the other libraries and dependencies that are installed in a system, it must be stable, it can't have any issues with version skew or backwards compatibility problems, and it must be upgradable. There always must be a way to move to the latest version of the system in order to consume bug and security patches. So that's actually a lot of requirements. And we didn't even talk about what OpenTelemetry does, actually. If you notice there, we are simply talking about the problem of allowing OpenTelemetry to do anything as a dependency on open source software. But we're going to solve these requirements because instrumenting open source software is worth it. This is such an important problem, and I have felt so much pain around this problem as an author of open source software that I'm really motivated to solve it. And I'm happy that we've done the effort. So how have we tackled this problem in OpenTelemetry? Okay, so let's start with composability. Separation of concerns is going to be our friend here. Library authors need to write instrumentation. The application owner wants to choose where that data goes, what format it's in, all of that jazz. So you need to take observability and decompose it into two separate pieces for these two separate audiences. We call this the API and the SDK. So library authors only touch the API, application owners only touch the SDK. The API contains all the tools you need for instrumenting libraries, which includes things like tracing interfaces and metric interfaces and constants for the semantic conventions that define common operations like HTTP requests. But you'll note the words interfaces and constants. You don't need implementations of any of these things to instrument your software. You just need the interfaces to do that. The implementation then is in the SDK, which contains all the tools you need for processing telemetry. So this is generally a bunch of plugins like span processors and exporters for different formats like Zipkin and OTLP and Prometheus, as well as all the different ways to configure all of this stuff. Then, to make the system work, you take the SDK and register it with the API when you start your application. Why does this help? Well, you can't create a dependency conflict if you don't have any dependencies, right? And since libraries only depend upon the API, and the API doesn't contain any kind of implementation, then the API has no dependencies. Therefore, libraries that depend upon the API have no dependencies. So there's always going to be a way to avoid a dependency conflict because the core bit that goes everywhere, the instrumentation API, does not haul in any dependencies. Now, you might ask, Ted, is this really actually useful? Isn't everyone just going to use the SDK anyways, so there's not actually a separation here in practice? No. The answer is no. This is really, really useful in the real world already. In fact, it's not just useful for avoiding dependency conflicts. It turns out there's a variety of reasons why having a different implementation makes a lot of sense. First and foremost, testing. When we're building OpenTelemetry, we found it very useful to create mock implementations of these APIs and use that in our testing. And we think these mock implementations would actually be useful to you, the end user, for testing the instrumentation in your application. Because actually testing instrumentation is somewhat important. It's important to know that your library is actually producing the correct data, especially if you're trying to conform to a standard of, say, what an HTTP request is supposed to look like. So this is really useful. So what if you don't care? What if you've written instrumentation in your library, but the application owner has never heard of OpenTelemetry and they don't install any implementation? Well, no problem. A no-op implementation comes with the API and it has no overhead and causes no problems. So if nothing's installed, it's a no-op. Easy. Speaking of overhead, what if you really care about performance? Well, if you're running in a scripting language or a single-threaded language that has foreign function calls, you may want to use the C++ implementation of OpenTelemetry. OpenTelemetry comes in C++. You can take that C++ implementation and bind it to the API in Python or Ruby or any other language where that speed boost might be of use to you. You also could bind it potentially to the Rust implementation because we've got one of those. So there are performance options here that don't involve anything that looks like a hack. You just write an implementation that uses foreign function calls. Well, what if instead of performance, you care about compatibility? C++ dependencies are not for everybody. You may be running on top of a platform that doesn't use C++, like some versions of Python. And this would be a real pain in the butt if that was the only solution we provided people. So in these cases, you don't use that implementation. You use the native language implementation that we provide in every language. Finally, what if you're just a weirdo? What if your system has just weird requirements that mean that our awesome standard SDK framework that we think is so great simply doesn't match? Well, in those cases, you can create a custom implementation. One real-world example here is Envoy. Envoy is an awesome service mesh that all the kids are using these days, and it's very performant, written in C++, but it has strict requirements around the architecture of anything that gets plugged into it. Specifically, they require that all of their dependencies be single-threaded. That's not necessarily a bad architectural choice, but when we write our C++ implementation, we want to make use of the fact that there are multiple threads available. Well, they're not going to accept a multi-threaded implementation. We could try to take our framework and make it somehow work both single-threaded and multi-threaded, but the confusion and overhead that comes from that kind of flexibility sucks. You don't actually want to take one framework and stretch it that far. So instead of doing that, we just wrote a single-threaded implementation for Envoy to use. Problem solved. This is a good design principle for anyone writing a framework. You want to give people a solution that works for the common cases, but you shouldn't be so presumptuous that you think your framework can make everyone happy all the time. There's never any one single solution that's going to stretch all the way out to the edges. There's always going to be edge cases where some other solution is going to be better. All right, design aspect number 3, stability. We know that we want backwards compatibility, but we want to keep adding functionality to OpenTelemetry, of course, right? Like there's always going to be new kinds of signals, new kinds of data we want to admit, new cool features that we think would help people. So we want to add those, but we don't want to break the APIs that we've already given people. So the solution here is to say that APIs that have already become stable only make additive changes. In other words, stable APIs always have to be backwards compatible. The way you make something backwards compatible is to not mutate it. In most languages, there are ways to add additional functionality to existing packages that don't break backwards compatibility, but it can be a bit sketch. And so you just want to say that as long as it doesn't break backwards compatibility, it can be added. For everything else, you put it in a new separate package. So experimental APIs obviously have to go in a new package because they're guaranteed to break. If something's in alpha or beta, we're still playing around with the design and we want feedback, that thing is going to mutate. To allow that to mutate and break without affecting the stability of the other APIs we've already given to people, we take our experimental APIs and put them in a new package. Why does this help? Well, if you never break the API, you're never going to break anyone calling the API. Again, that seems obvious, right? However, this happens all the time. I'm always encountering software that breaks its public APIs and just says, sorry, new version. We followed Semver, so it's now 3.0, so that means it's fine that we broke all your stuff. This is not true. It might seem like a good idea to iterate fast and just version your major version number, but what actually takes longer? Doing some careful design up front to ensure that your APIs stay stable even in the face of added functionality, or forcing all of your users to fix all of their references. And with something like instrumentation, we're talking about a lot of references, like API calls in the millions. That's what it means for people to instrument all of the software on Earth. It's tons and tons of references. So the effort it would take to fix those references because we wanted to break an API is totally untenable. And there are definitely other domains which have the same requirement. Okay, last but not least, upgradeability. Security patches, you gotta have them. Fortunately, our prior design points have solved this problem a bit. If the API never breaks instrumentation, then the application owner can always upgrade to the latest SDK because the latest SDK is going to work with all of their existing instrumentation. So that's great. However, the SDK also has to be careful not to break its plugins. Therefore, the SDK must support old plugin interfaces. How does this help? Plugins won't block you from upgrading if you don't break them. Again, this seems obvious. However, in practice, I've encountered many of frameworks that I've had to depend upon that mutate their existing plugin interfaces, meaning they come out with a new version of the framework where the existing ecosystem of plugins doesn't work and won't work until all those plugin authors go out there and update their plugins to work with the new version of the framework. Don't do this to people. Instead, create new versions of those interfaces while still supporting the old versions. Frameworks that break their plugin ecosystem are hell. I've had to live in this hell. Hell is choosing between an old version of the framework or having to rewrite old plugins so that you can update and get that security patch. I've had to do this more than once, and I should never have to do this. Okay, so what's the point? The point is that none of what we just talked about was specific to observability. What makes OpenTelemetry awesome isn't just the fact that it provides better indexing than you can get out of any other observability system. It's also that we care about all of these other design requirements and we care about open source software. If you create dependencies for other people yourself, you should also care about this. So please consider how to make your own software composable, stable, and upgradable. Think about the design principles that we've laid out in this talk, because these really are design requirements. These aren't features that you can tack on later. If you don't architect your software from the beginning to support things like upgradeability and avoid things like backwards compatibility issues in their interfaces, you won't be able to do it in the future. So you have to support this stuff up front. So in conclusion, don't break the people using your software. Don't break the people providing value for your software. Don't create versioning and dependency hell on anyone near your software, and use loose coupling to keep things separate and clean. If you follow these design principles, that means your software can go anywhere, which means the amount of good and joy your software can bring to the world is that much more. So I hope that was interesting. Thank you very much. If you like the design principles in this talk, give me a holler. If you hate them, also give me a holler. I'm on Twitter, Tetsuo. Enjoy.